Hello everyone, my name is Brendan O'Connor and I'm going to present to you my exploratory study on perceptual spaces of the singing voice. This research was supervised by Simon Dixon and George Fazekas and was conducted at the Centre for Digital Music at Queen Mary University of London. So to talk about the motivation behind the study, I come from a background of music electronic composition and was quite interested in using the voice as my medium of timbral deviation and kind of using it more as an instrument rather than a narrative element in music. And so I was kind of very interested in the question of how do humans hear different characteristics of the singing voice. There's been a lot of disagreement and inconsistency regarding the terminology between voice specialists, and this is often due to the fact that we come from different angles of analyzing the voice, whether we are performers or artists or scientists. So I think having some kind of global timbral space of the singing voice and all its different characteristics, singing styles and so forth, would be quite useful. That could converge all this terminology together. But one thing about timbral space is one of the questions is how does it change in relation to certain conditions, such as is the singer male or female? And are they singing at a high or a low pitch? Does the identity of the singer drastically change the timbral space in general? And also from the other's perspective, how does timbral perception relate to different participants? So we'll explore those questions throughout the study. And in terms of singing synthesis, which is something I'm quite interested in, having timbral maps would be excellent to use as part of a regularization term that would teach the neural network how humans hear different characterizations of the voice and encourage a similar latent space upon which it could model the voice. So the procedure for the experiment, basically, if we start off getting pairwise dissimilarity ratings, and this is done by getting listeners to listen to two recordings of, in this case, different singing techniques, and then they rate similarity or dissimilarity between those two singing techniques. And we do this for 120 pairwise comparisons and format or compile these dissimilarity ratings into a matrix. And these dissimilarity matrices can then be used for clustering analysis, which will teach us, which will kind of show us how participants perceive the human voice, how they cluster together, and what their relations are to one another. And this can be seen visually using multidimensional scaling techniques, which allow us to kind of get more of a global view of how the structures of singing techniques move around each other and how well they group together in a 2D or 3D space. The vocals, we use vocal set as our data set for this experiment, which basically consists of multiple singers singing a variety of musical exercises in different singing styles and pronouncing different utterances as well. So this is quite suited for our means, given the ground truth class labels related to style. And we basically sample it. Here's a diagram of the sampling hierarchy for one singer. Well, first of all, we randomly select 3 males and 3 females from the vocal set dataset, and we generate 2 sets for each singer, each set relating to a low register or a high-pitched register. And within each set, we look at 5 different vocal techniques. I'm not sure if you're going to hear them now, but I'll play them for you anyway. See if we can. So those are examples of straight, belt, breathy, fry, and vibrato singing styles or singing techniques. And for each example, we extract 3, or for each class, we extract 3 examples, giving us a total of 15 examples per set. However, I should note that, or one should note that we did have an error with data collection, so we've only been using 14 examples instead of the 15 to produce our results. And just to give you an idea of what the instruction was that was given to participants, to quote it, it is, "Your task is to rate how similar or different the singer's sustained vocalizations sound to you due to different singing techniques. The challenge, therefore, is to rate vocal similarities irrespective of the singer's changes in pitch and utterance between recordings." And just underneath we can see a snapshot of what the interface was, where participants would click on the reference button to hear the reference recording, and then they have 8 buttons to play each comparative audio clip, and then they can rate the similarity or dissimilarity. They can rate how similar or dissimilar each audio clip is to the reference clip, and that gives us our ratings. Now, to talk about perceptual data clustering, so when we think about the data that we get from participants, we want to know how it clusters together, and do these clusters relate to the ground truth class labels as well. So first of all, we wanted to see what the best number of clusters were to represent each participant's data. And we determined this by basically using 2 methods, the elbow of sum of squared error plots and the silhouette scores. So these graphs here on the right are in reference to sum of squared errors, which basically give us an idea of within cluster variance. So they tell us how compact or how non-compact those the clustering behavior of perceptual data is. And normally we would select an elbow point when we compare the SSEs against each potential number of clusters, and choose the point where there's an elbow in the graph. So we can see that 2 or 3 is a good turning point here, but it's still ambiguous whether it's 2 or 3. And in another participant's data, there was no elbow point whatsoever, hardly none at all, and it's kind of very hard to pick an optimal k-value or number of clusters to represent their perceptual data. So due to these ambiguities and uncertainties, we decided to work with the silhouette scores as a measure for determining the optimum number of clusters. This was representing the SSEs, but over here we have the optimum k-values based on silhouette scores. And we can see that number 2, which isn't a fantastic number, but it does seem to be shown in the data, that participants' data was best represented through 2 clusters. So we're going to use that in the upcoming analysis. Cluster metrics between conditions. So we compared several clustering metrics of participants' perceptual data between 3 conditions of singer, register, and gender. And we based these clustering metrics using k equals 2 and k equals 5. The clustering metrics we used, as before, are SSEs, silhouette, and accuracy, which in this case compares the combination of cluster assignments against the ground truth class labels. So basically kind of figuring out how correct the participants' clustering behavior was. And so below we have on the left of this table the number of clusters used in each experiment, the variable that was being measured, or the clustering metric that was being measured, and these 2 columns here, the columns on the left here represent the condition that gave us higher accuracy, and the labels on the conditions on the right show us which ones were lower. So we can see that male 2 in this example has a very, very low accuracy rate, especially in comparison to the majority of the other singers. So that's for k equals 2, and we can also see similarly it's also got the lowest mean value for k equals 5. So that's telling us something about the male 2, the perceptions of the male 2 sets, that maybe that it didn't quite induce a lot of robust clustering structures. And on the other side of things, female 5, for example, seems to have the highest, not the highest mean, but the highest distribution of accuracy scores in comparison to male 1. And what else can we can also observe that we did test for singer, register, and gender conditions, and yet the only differences that came up for clustering metrics were in relation to singer identity. So that tells us something about gender and register, that they do not necessarily predict whether a perception of the voice is going to be well clustered or not. Moving on to participant information and clustering metrics. As I said at the beginning, we were also interested in understanding how conditions relating to the participant affected clustering performance. So we did this for we got correlations between participant clusters' performance metrics for k equals 5, because that is the ground truth, the number of ground truth labels, and compare this to profile information. I'll talk more about this actually towards the end of the presentation, where I can make some general statements about it. But basically, perceptual abilities came from a questionnaire based on gold MSI questions, and we saw that there wasn't much relation there wasn't much correlation between this and clustering metrics, which implies that these questions were more based for musical contexts rather than sonic context or sonic evaluation. Let's move on to Tombrell spaces. Excellent. Finally, we analyzed the average distance ratings between all ground truth classes grouped by condition. So we can see we have different class pairs here, and these represent the means of the distances between those two classes. And we have the Tombrell spaces up here, generated by multidimensional scaling. However, it should be noted that with multidimensional scaling, it does not take into consideration interclass variance. In this case, breathy to breathy or vibrato to vibrato comparisons. There was a lot more interclass variance in females than there were in males. Taking a look at distances in relation to register conditions. So for the low register, the distances between these different classes of string straight to belt, belt to vibrato, and fry to vibrato were much larger in the lower condition and in the lower register than they were in the higher register. Also, we can observe that when we compare the genders, that straight to breathy is much larger in males than it is for females, and vibrato to fry is much larger in females than it is for males. Now these distances are, we can see clearly the difference between straight and breathy, that it's much larger in males than females, maybe a little bit harder to see between fry and vibrato, but it is there. And also we can witness the tendency for clusters to occur between straight, belt and vibrato, while fry and breathy classes seem to be quite segregated from these clusters, and it's kind of common throughout the tests there. We were a bit concerned about the noisiness of the data, as we saw in the SSE measurement graphs earlier on. There was not a lot of clustering behavior as one would have expected. And this could be due to a number of confounding variables. When participants gave us feedback on what influenced their dissimilarity ratings, they mentioned things like performer's lack of control, distortion, temporal pitch variation, total amount of notes per sample, melody, and assumed class types. And there are also some issues with the vocal set utterances that we used as well. So there's a few considerations taken there when considering how robust our data is against noise. To draw some conclusions, I would say that overall participant data was not easily separated into clusters beyond 2. Conditions of gender or register did not actually affect the cluster's robustness or perceptual agreement with ground truth labels. So that was quite interesting. Participants with more musicianship relevant to singing were likely to perceive singing styles similar to the ground truth. And we have shown how Tombrell maps differ between genders and pitch register. In future work, we are interested in using the feedback we've taken from participants to revise the setup of the listening study, and hopefully give more robust data with less noise. We could also filter out participants by inconsistency and task comprehension, which have proven to be fruitful metrics that predict how accurate and how well cluster structures remain for participants. Including the acoustic parameters for each recording would also be of great benefit to us, as we can combine this with clustering techniques and multidimensional scaling to understand why it is we perceive certain classes to be very similar or very close or very dissimilar to others. And finally, with the Tombrell maps, we can actually use their coordinates as part of a regularization term when training neural networks to develop a latent space, and this would encourage them to model the voice in a way that mimics human perception. That's about everything. If you have any questions, I'd be happy to answer. Thanks very much.